All right. Good morning. My name is Eric Rhodes. I'm a civil engineering master's student working with my co-author and advisor, Dr. Sale, to finish up my thesis this May. This presentation is a simplification of my thesis. We will be exploring methods for analysis of contaminant mass in place, in transmissive and low K zones. We are moving into the subsurface world with contamination present across heterogeneous subsurface media. This figure shows the general nature of the subsurface contamination. The contamination, oils, gas, diesel, etc., has moved down through the transmissive zones to rest on the water table. Natural degradation produces gases, and at higher concentration, the contaminants diffuse into these low K zones. And these low K zones have been historically difficult to remediate. In this thesis, we analyze 31 different cryogenically collected boreholes, and these are simple visual examples of what the snapshot would look like. There are four main objectives of this thesis. The first is to visualize current cryogenically collected data in gINT. The second is to compile data from 31 different boreholes across 7 unique sites in the US. The third is to provide methods to compare mass in place and transmissive and low K zones internally in a site, intra-site, and across sites, inter-sites. The final objective is to explore opportunities to analyze cryogenically collected data. The content of this presentation will include a brief description of methods, selective description of intra-site results, selective description of inter-site results, and concluding remarks. A quick background. Borehole sampling through early methods was essentially single sampling from monitoring wells with graph samples. Resolution was in meters or more, which really isn't enough. Modern methods like subsurface profiling and core extraction has allowed for continuous resolution, but has limitations. For example, profiling a borehole is done after modifying the subsurface media through drilling, and sediment core extraction has pore fluids drained from gravity. Cryogenic core collection as a next generation technique looks to solve many previous problems, even with its own limitations. This is a figure that describes the basic process of cryogenic core collection. A hollow stem auger is advanced to required depth. The liquid nitrogen is injected and initiates a phase change in the subsurface media. This takes 4 to 6 minutes to freeze. It is fast enough to preserve microbial markers and gases and liquid in the pore space in position even when the core is removed. The core is always kept frozen at -80 degrees until processed in a lab. It is effective down to 40 to 50 feet, but can only be used in subsurface media that is smaller than the diameter of the drive shoe. Here it shows the core frozen. This picture is the extracted core being cut by a chop saw under a hood in a lab. To the right is an example of a 1-inch sample with its plastic liner still intact. And cutting the core is much like cutting concrete for anybody out there who's done that. Each sample ID has 2 1-inch pucks that correspond to a singular depth interval. Subsample A is for microbial purpose, subsample B is for contaminant concentrations, subsample C is for geophysical purposes, and subsample D and any remaining core is archived in a -80 degrees freezer. Subsample C is visually classified by professional geologist Dr. Sale for sediments. As you can see here, the jars each contain a single sample ID and are individually classified. They are then put in under UV light for fluorescence. A key point to this thesis is to differentiate between transmissive and low K zones through relative difference in sizes of subsurface media. This relative difference defines some subsurface media as transmissive and the rest as low K. The dividing point for each site was defined from our sample core analysis and through historical information. We found that there are 2 different types of sites sampled. The first type of site has predominantly sandy subsurface media. This defines all sands as transmissive and all silts and clays as low K. The second type of site has predominantly silt and clay subsurface media. This defines all sands and some silts as transmissive. It then defines the remaining silts and clays as low K. This thesis presents the dividing point between the transmissive and low K zones as academic and with limitations. Next, I will continue into my results with figures while introducing equations that apply to them and further the analysis. First, I want to point out the USCS graphic legend for the subsurface media, then some quick definitions. NAPL is a non-aqueous phase liquid and includes total petroleum hydrocarbons. TPH is the addition of gasoline range organics and diesel range organics. Here is a standardized gINT graphic. Starting from the left side, looking at data by depth, we have the depth from ground surface, sample ID, sediment color, USCS graphic log corresponding to the legend, NAPL fluorescence with light gray meaning nothing, and then the lighter grays increase with increased fluorescence. The transport column, gray or black is low-K and blue is transmissive. And the water table data is also plotted by depth with whatever is available. You will notice that recovery is not 100%, and this varies from borehole to borehole. Next, we have concentrations in milligram per kilogram of methane, TPH, benzene, DRO, and GRO. The next column is the percent ratio of benzene to TPH. And then finally, we have saturation percentages of gas, water, and NAPL, all plotted by depth. The equations here use data in this graphic. The first equation determines the mass in place for each sample ID. It multiplies the concentration, milligram per kilogram, by the depth that is associated with the sample ID, and then multiplies it by the bulk density. We calculate the bulk density using our calculated porosity, along with the density of quartz. The mass associated with each sample ID is then summed for all sample IDs in the borehole, and the value is the total mass of contaminant in the borehole, and this is printed right here. Continuing with equations, the total mass of contaminant in transmissive zones is calculated by selectively adding data for all sample IDs in transmissive zones. The low-K analysis follows the same calculation. This produces the mass of contaminant in transmissive and low-K zones. Here's a graphic for the total mass in place for all boreholes sampled from site B. It is on a log scale. Starting on the left, the light red is benzene in transmissive zones, then benzene in low-K, TPH in transmissive, TPH in low-K, methane in transmissive, and then methane in low-K zones. This is hard to read because of the 6 variables and the range of mass in place. The log scale is completely necessary, but it really takes time to understand how significant these masses are comparatively. The blue triangles here indicate that these boreholes are sampled as a triplicate, so they were sampled near to each other, and then the black triangle indicates that this was sampled with non-cryogenic purposes near the other 3. Next, we need to process this data to be more readable and comparable across sites and boreholes. These are the equations applied to the total mass of contaminant in place. They're fairly simple. Equation 8 is the percent of contaminant in transmissive zones, and it is equal to the total mass of contaminant in transmissive zones divided by the total mass in the borehole. And this is multiplied by 100, and then the process repeats itself for low-K. Next, these are the equations used to define the percent of the borehole that is transmissive or low-K. Equation 6 is the percent of sample borehole that is transmissive and is equal to the length of borehole defined by transmissive zones divided by the total length of sample boreholes. So length transmissive divided by length sampled. The calculation is then repeated for low-K zones. Here we have a graphic for the previous equations. It is the percent mass of contaminant in place for each borehole at site B, which is located in glacial outwash. It is on a 0 to 100% scale. There is a very broad range of results. Lighter colors represent transmissive zones. You'll notice here that these 3 boreholes were all found to be completely transmissive over their sampled intervals. To help explain what is being said in this graph, I will look at the data for borehole B3. This states that 40% of the borehole is low-K, 5% of the total mass of benzene is in low-K zones, 4% of the total mass of TPH is in low-K zones, and 19% of the total mass of methane is in low-K zones. B3 has contaminant preference for transmissive zones, where if we look at B1 over here, it shows contaminant preference for low-K zones. Data is importantly now on a y-axis scale that allows a wide range of contaminant mass to be compared across sites and boreholes. Next, we need to be able to compare hydrocarbon and chlorinated solvent sites. This is a simple calculation that sums total mass of each contaminant in the borehole. Hydrocarbon sites sum TPH and benzene, and chlorinated solvent sites sum the chlorinated solvents PCE, DCE, TC, and VC. Those are just acronyms. Equation 10 is processed through equations 4, 5, 8, and 9 to produce the percent of total mass of contaminants in transmissive and low K zones. This variable can be used to compare chlorinated solvent sites and hydrocarbon sites. Next, to inter-site comparisons. Here is a figure for the total mass of contaminants in place for chlorinated solvent sites. The dark color for the first bar is the percent of borehole that is low K, and the dark color for the second bar is the percent of the total mass of contaminants in low K zones. What we found to be important, which is also apparent on the next slide, and I warn you that this next figure graphs all the boreholes from the thesis together, so it's a little intense. We really want to understand the difference between the percent of the borehole that is low K and the total mass of contaminants in low K zones. And where there is this larger difference here, 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 this is what is significant. And we want to calculate that difference between the columns, but also apply a statistical analysis. And that leaves us to equation 11. Equation 11 is the difference between equation 7 and equation 9. As mentioned before, it is the difference between percent of borehole, that is low K, and percent of total mass of contaminants in low K zones. The calculations produced from equation 11 imply that a negative number prefers low K zones and a positive number prefers transmissive zones. And here we go. As mentioned before, there is transmissive zone preference here, and there is low K zone preference here. From our statistical analysis, we were able to determine the standard deviation from the mean, so we can possibly say that a borehole exhibits statistically significant preference towards one zone or the other. For example, my thesis presents this statement for borehole C1. Borehole C1 has a total mass of 127,000 kilograms of contaminants per acre and 114,000 kilograms of contaminants per acre in low K zones. Borehole C1 has 61% of the borehole defined as low K and 90% of the total mass of contaminants in low K zone. This is a 29% unit difference. Using the statistical analysis, the contamination at borehole C1 shows a statistically significant preference towards low K zones. And these types of statements can be made for each borehole, each one of the 31 boreholes. And so this gives total mass in a borehole, total mass in transmissive and low K zones, percent of total mass in transmissive and low K zones, and statistics for zone preference that help develop an understanding that is comparable to other boreholes in a site, but also across to other sites. So overall, I was able to meet my objectives. I created essential standardized gINT graphics, and these were all automated. Next, the data strongly suggests that analyzing mass in place in transmissive and low K zones for intra and inter-site comparisons is possible. And ultimately, I presented a set of information that could be used to decide remediation activities and their post-remediation effectiveness. Limitations. So the sediment is visually analyzed with no technical experiments, and this is done because of the contamination of the soil and the time involved. It is also important to note that these methods only apply to the boreholes and not to the overall site. That is very key. It's only a borehole analysis, not a site analysis. Future work would be to add any additional data by depth. Here you have aqueous properties, more contaminants, NSCD byproducts. We have a whole bunch of microbial data. Next, we want to keep adding new sites to the inter-site analysis, possibly include a hydrocarbon site with pre and post remediation data. And finally, we really want to expand the methods to include some sort of standard geophysical classification technique. I would like to give a special thanks to the CCH staff and others, along with my sponsors, and a special thank you to CSU and One Water Solutions Institute for making hydrology days happen today. Thank you so much, and are there any questions?
Great, thank you, Eric. So for anyone that may not have been on at the beginning, you can enter questions into the chat queue, or you can raise your hand and I will be happy to turn your microphone on. Just give it a second or two here, see if we get anything in the queue.
Of course. Thank you for listening, everybody. I know it was a lot.
All right, so we have a question from Tom Sale. I'm going to see if we can turn on his microphone.
I believe that's my advisor.
Let's see. Try something. Okay, Tom, I turned on your microphone. Let's see if that works.
Hello, can you hear me?
Sure can.
Hello. Oh, good. That's amazing. Hey, I'm going to echo Eric's comment. Thanks for making hydrology days go live. It's remarkable. I'm sure it wasn't easy. My question to Eric was these calls on transmissive and low K zones are super important for remediation, but we're doing it based on visual logs. And I was wondering if Eric could comment on whether you could put the cores in a permeameter and measure the permeability directly?
Yes, so that is one way that we can look at it. We take the frozen core and we do what Tom just said, and it actually gives the permeability. One of the difficulties we had was just the cost of doing that for every core, but that is absolutely possible.
Thanks.
Thank you, Tom. Any other questions?
I haven't seen anything yet. Maybe we'll give it another 10 or 20 seconds in case there's a lag.
And thank you guys for setting this up. I really do appreciate this, being able to present.
Yeah, I'm glad we've had so much interest. Just on a personal note, I've run many webinars during my time with the One Water Solutions Group, and this is the biggest webinar I've run. We have 60 people on right now, which is just fantastic. So thank you to everybody for tuning in. That makes it so much more meaningful for the presenters and everybody involved in this event.